Hi, everybody. Welcome to our introduction to solubility notes. So, solubility is basically how well something dissolves in water. That is what we're going to be talking about, and we're going to be looking at all sorts of facets of that. And so, let's start by talking about water. How much water is there? There's a whole heck of a lot of water, but where is it located? So as you can see, nearly 3/4 of the Earth's surface is covered by water, but 97% of this is salt water, with the other 2% being locked in ice caps and glaciers. That means only 1% of the world's water is what humans are using. So how much do we actually use? A person can live a month without food, but only a week without water. We have got to have water. Average U.S. water consumption per person is 50 gallons a day. The U.S. uses more water than any other country, and 90% of the water that we use is for industry and agriculture, so farming. So why is water so important? We call it the universal solvent because of how it behaves with other molecules. So water's molecule forms a V. It makes this shape with oxygen being at the base and two hydrogens making up the two legs there. Oxygen is the negative ion, the two hydrogens are positive ions. One end of the molecule therefore becomes slightly more positive than the other end. So the hydrogens being your positives are going to make the water molecule having one side being more positive and the other side being more negative. Okay, this causes us to have a polar molecule. In your notes, you should record that water is a polar molecule because one end is slightly positive while the other end is slightly negative, or it has an uneven distribution of charge. Okay, this polar characteristics of water is the main reason that makes water such an excellent solvent, and we're going to delve into that right now. So, water, because it is so polar, is able to dissolve many ionic compounds because ionic compounds are extremely polar themselves. So ionic compounds can dissolve in water. And this is because water, because of its uneven distribution of charge, can break apart ionic compounds based on the attraction of charges. So the negative oxygen is going to, side of water is going to attract the sodium, the positive ion, whereas the positive hydrogen side of the water is going to attract the negative chlorine of sodium chloride. So the charges in ionic compounds make them be able to dissolve in water. Other things that dissolve are molecular compounds, which can be also defined as covalent molecules if they are polar molecules. Molecules that have uneven sharing of electrons make them polar molecules. In other words, molecules that are not the same on all sides. Molecules that have a lone pair are all considered polar covalent compounds, and these compounds also dissolve in water. That leaves us with, okay, why is water so able to behave so weirdly? And it has all to do with polarity. The only thing water does not dissolve is nonpolar things. So water dissolves polar things and ionic things. Anything that is nonpolar or which is symmetrical or does not have lone pairs, those are things which cannot be dissolved by water. All right. Another keen or interesting fact about water is that water is one of the only substances that becomes less dense than its own liquid state, and that is because water molecules actually form an air pocket in between the way their molecules come together, so they are able to be less dense. I think my next slide shows that. There we go. So molecules in the solid liquid water are linked by hydrogen bonding. So you see all those molecules in that picture sort of looking like they're sticking together. They're actually just highly attracted to each other. And you'll notice they are attracted in the negative to negative to positive format. And so between these 4 to 8 molecules, when they make up a group, there is going to be a section in the middle here that forms and causes the water molecule to take up more space, more volume. It expands in volume. Anybody that has ever placed a can of soda into the freezer to get it colder and forgot it there is probably knows exactly what happens to something that is almost completely made of water in the freezer. The volume expands and the can of soda explodes. So this makes water less dense and allows the ice to float. In other words, it becomes more buoyant. Physical properties of water. We know things that at room temperature, water is transparent, it's odorless, it's tasteless, it has no observable odor, and you know not to drink it if it does have an odor, because something is wrong with that. We also have water having hydrogen bonding, and which causes it to act interestingly like having surface tension, and being able to have there be the idea that things could actually float on top of water, if not because they are less dense, but because they can take advantage of the surface tension. In this video, we're going to try to see an animal called the Jesus lizard, also called the basilisk lizard, that is able to take advantage of water's surface tension and be able to, as you're going to see, run across the water. Here we go. Let's look at that one more time. Here he goes. He is running across the water. Here we go. Okay, so he is able to run across the water like that, not only because he's going super fast, because really honestly, if humans could go super fast like that, we would try to run across the Atlantic Ocean. We do not have the ability to do this because of several reasons. It's not because of water surface tension. We would need water to have a greater amount of surface tension to support our weight. So it has to do with our weight. It also has to do with the fact that he, as the lizard, also has a tail out behind him that is a counterweight, so he doesn't fall flat over forward. And he also has webbed feet, which give him a greater surface area to take advantage of greater surface tension of the water. So let's watch that one more time. Okay, so we are going to go back to our notes and go forward here. Okay, so what is happening is the thing basically for you to remember is that like dissolves like. That means polar dissolves polar. When we talk about how liquids mix, if they have a different polarity, they will never mix. We call liquids that will not mix immiscible. That is the terminology, immiscible. Oil and water will not mix, not because oil is less dense than water, but because oil is nonpolar and water is polar. So how does dissolving happen? You will want to make sure you have the table drawn into your notes for this. So dissolving occurs at the surface of a solid. So if we have a solid and we're placing it into the water, it dissolves at the surface, from the surface of the solid inward. Our solvent molecules will cluster around the solute, which is the name we give the solid in solubility terms, and it begins to break down the outer shell of solid and works inside. The negative end of the solvent is attracted to the positive ends of the solute, just like you saw in previous pictures, and the solvent molecules spread the solute out equally throughout the solution. So, what happens if we stir it? If we have a solid solute, stirring actually increases our dissolving. If we have a gaseous solute, that actually decreases the dissolving. You can check that if you want to by pouring some Sprite into a cup and observing all those gas bubbles. If you were to go stir the Sprite up, more gas bubbles would float to the top. Heating increases the dissolving of a solid by increasing the kinetic motion of the solute, breaking down the solvent. However, heating affects the gaseous solute by decreasing dissolving. If you've ever had a soda on a hot summer day and left it outside, it goes flat much more quickly than if you kept the soda in the refrigerator. It would stay bubbly for a little bit longer. What about pressure? Solids do not experience any difference in their solubility based on pressure, but gases do. If we keep something that has a gas in it under pressure, then we are keeping the gas in the solution. Just think about that soda can again. We keep it closed in the soda can so that we can keep pressure on it and the bubbles stay inside the liquid. The minute we release the pressure is the minute the bubbles start coming out of the liquid. What about increasing surface area? If we were to take that solid and break it apart, then what we would find is that we would be able to dissolve it more quickly because more solvent can touch the solute. Gases, this does not affect. Surface area does not affect gases. So you need to make sure you have this table written into your note. We are specifically going to talk about what exactly does this terminology solubility mean. When we're talking about solubility, we're talking about the amount in grams of the solid solute that can be dissolved in a given quantity of solvent, usually water, at a certain temperature. Now, can we have a gaseous solute? Yes, we can. Then the gaseous solute would not be solid. Obviously, it would still be measured in grams, though. Can we have a liquid solute? Yes, we can. The liquid solute is always the solute that is the species that is present in lesser quantities than the solvent, which would be present in greater quantities. Okay, so how is solubility expressed? We've already said grams of solute per 100 grams of water, and we would have to state the temperature. So the solute grams, the grams of water is the solvent, and the temperature at which we are talking about. By changing the temperature, we would be changing the amount of grams of solute that can dissolve. Because remember, we've already mentioned that solid solutes become more soluble, so more can dissolve at higher temperatures, whereas gaseous solutes become less soluble at higher temperatures. Okay, so we have three terminologies. You need all three to be written in your notes. The first terminology is called a saturated solution. A saturated solution is reached when no more solute can dissolve into a solvent at a given temperature. We have reached the point at which saturation has occurred, and now any more solute that we put into the container with the water in it will just simply sink to the bottom. You have seen this before if you've ever made sweet tea and stirred and stirred and stirred and stirred and added more sugar, but no more sugar will dissolve. Instead, it just sits at the bottom. An unsaturated solution is a solution that contains less solute than a saturated solution. In other words, that means that I could still add more solute to it. That sweet tea could still have more sugar dissolved in it. These, and you're going to see as we refer to these, we're going to refer to these as they are found on a graph. Finally, a supersaturated solution contains more dissolved solute than a saturated solution. Now, let's still use that sweet tea analogy. In the sweet tea analogy, if we want more sugar to dissolve, anybody who's ever made sweet tea knows that you have got to warm up the tea and get more sugar to dissolve in the solution, and that makes it sweet tea. That keeps the sugar dissolved in the solution longer, and it makes a much more or a much sweeter juice or drink for you to have. So let's take a look at this in terms of the graph. Here is a solubility graph for potassium chloride. As you can see, solubility is increasing as temperature increases. We can say that solutions are described by the line. That line represents a saturated solution, the point at which no more solute can dissolve at a given temperature. And so we've drawn a line to connect all those points at the different temperatures. But what if we make a supersaturated solution right now? This is where we heat it up to a higher temperature, get more to dissolve, and then allow it to cool back down. Any solutions that have more solute dissolved and thus have their solubility higher than the line are called supersaturated solutions. And then solutions that have not enough solute dissolved yet, they could still dissolve some more, are called unsaturated solutions. And this is where their solubility is below the line. Okay, so what is a supersaturated solution? So this again is where we have a room temperature solution. These are our molecules of the solute that have all dissolved. And then we heat it up and we add more molecules to the solution, get those all to dissolve, and then we allow the solution to cool back down to room temperature, keeping the more molecules dissolved. This is a supersaturated solution. By definition, it is a solution that has more solute dissolved in it than a saturated solution at the same temperature. All right, so oftentimes we have to be able to draw a solubility curve. Let's go back one, where we are thinking about a change in the amount of water. So let's talk about that a little bit. What if we change the amount of water? How does this change the solubility? Okay, so think about it. If we make 1 pack of Kool-Aid, we will need 2 quarts of water. What if we make 2 packs of Kool-Aid? Well, then we need to double the amount of water to 4 quarts of water. Or if you like me, you like a really, really nice sweet solution of Kool-Aid, and that's why I'd put 2 packs in 2 quarts of water. But that's a taste thing. That's not a how am I supposed to make it. If I wanted to have the same concentration, I would have to double my amount of water. So doubling my solute means doubling my solvent. So that is exactly what is determined here. As long as we keep the temperature the same, if we double the solute, we have to double the solvent as well. What if we don't have enough solute? In order to reach saturation, if we do not have enough solute, we must add more until we reach the saturation line. For example, if the solubility is 30 grams per 100 grams of water at 50 degrees Celsius, and we only have 25 grams of solute at 50 degrees Celsius, then we need 5 more grams. So we would have to add 5 more grams to reach the solubility line, which means to reach the saturation point based on the graph. And we have reached the end of our presentation.